Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are taking a deep dive into capacitors and capacitance. This is a really critical part of Unit 2, electrostatic potential and capacitance. And our mission, as always, is to give you a simple, exam-safe explanation that you will, I promise, remember for life. So let's start with something you've definitely seen. Have you ever noticed a camera flash? It takes a few seconds to charge up. You hear that little whining sound. And then zap. The light is instant. It's incredibly powerful. My question is, why can't the normal battery in the camera just do that? Why does it need this whole separate mechanism?
Yes, I've definitely noticed that whine. I always thought it was just warming up or something. But why does it need that? Can't the battery itself handle that instant power dump? It seems a bit slow.
Exactly. You've hit on the key difference. The battery is a marathon runner. It gives steady power over a long time. The flash needs a sprinter. That sprinter is our topic for today, the capacitor. It's designed precisely for that instant energy delivery. And here's something really interesting about it. A capacitor, at its heart, actually blocks DC current. Direct current cannot pass through it because there's a physical gap. But it allows AC current, alternating current, to sort of appear to pass through it because it's constantly charging and discharging.
Wait, that is fascinating. It blocks one type of current completely, but lets another kind sneak past. Okay, we definitely need to unpack how this little magical component works.
Okay, let's unpack this. At a zero level, if you forget all the physics for a moment, a capacitor is just an electrical bucket. Its only job is to store energy and release it really, really fast, much faster than a battery can. To understand this, let's use our primary analogy. I want you to think of a water tank's width. Imagine you're pouring water into a tank. That water you're pouring in, that's the charge, which we call conductance. As you pour water in, the water level rises, right? The pressure at the bottom increases. That pressure, or that depth, is the potential, or voltage, $5.
Okay, so water is charge and the water level is voltage. I'm with you so far.
Perfect. Now, the most important part, the actual physical width of the tank, its area. That is the capacitance. Think about it. A really wide tank that's a high capacitance can hold a lot of water, a lot of corals. Without the water level, $5 way too quickly.
Okay, so capacitance is just the capacity to hold charge without the voltage or the pressure getting too high.
Exactly. The capacity, $T, is purely a property of the device's size and shape. It's about how it's built. To get a mental image for this, picture this. Two of your hands pressing against a smooth glass window from opposite sides. One hand is pushing, that's the positive plate. The other is pulling, that's the negative plate. Your hands can't touch because of the glass, the insulator. But the tension or the stress you feel between your hands across that glass, that's the stored energy.
That's a great image. So the gap is crucial. That's why DC can't cross, but the energy is stored in that tension.
Precisely. Now let's connect that idea of tension to the formal language. Let us see how NSERT defines this and moves to the math. Could you read the definition for us?
Of course. From section 2.11, it says, a capacitor is a system of two conductors separated by an insulator. The ratio QVD rest is a constant. QD equals a zero there. NSERT fans the constant. So does that mean if I increase the charge, the capacitance just stays the same? That seems a bit counterintuitive.
Yes, and that is where it gets really interesting. This is a classic exam trap. If you double the charge $Q that you put on the plates, the potential dollar must also double to keep that ratio perfectly constant. $Q depends only on the geometry, the shape, the size, and the separation distance of those two conductors.
So even though $Q are in the formula, $2 doesn't depend on them. Got it. $2 is fixed by the hardware.
You've got it. Which brings us to the most common design, the parallel plate capacitor. Its formula is $0 ferc epsilon AD. This little formula tells us everything we need to know. To get a high capacitance, a big bucket, we need two things. We need a large plate area, $1, and a very, very small separation distance. The SI unit for this is the farad, symbol anything. But here's a fact that should blow your mind. 1 farad is astronomically huge. For example, if you wanted a 1 farad capacitor and you kept the plates just 1 centimeter apart, you would need plates that are about 30 kilometers by 30 kilometers.
30 kilometers?
Yeah.
By 30 kilometers for just 1 farad. Wow. That puts things into perspective. That's why all the capacitors I see in circuits are in microfarads or picofarads.
It's incredible, isn't it? It shows how powerful the electric field is. So, if engineers can't make plates the size of a city, they must have another trick up their sleeve to get high capacitance in a small size. And that trick brings us to the effect of a dielectric. If we can't change the area dollar or the distance dollars anymore, the only thing left to change is the stuff between the plates. The epsilon dollar part, which is for vacuum, If we place an insulator, what we call a dielectric, like glass or plastic between the plates, something amazing happens. The material doesn't conduct, but its molecules, they polarize. They stretch or rotate a tiny bit in the electric field.
So the material is still neutral overall, but inside it, all the little positive and negative charges have shifted slightly.
Exactly. And this tiny shift creates an internal electric field that actually opposes the main field from the plates. So the net electric field, the total field inside, gets weaker. And since potential dollars is directly related to the field, if all dollars also drops. Now look at the formula. $2 is directly for the plates, but the voltage dollars have dropped. What must happen to the capacitance, the dollar?
The denominator gets smaller, then Cell must get bigger. So stuffing material in there lets you store more charge at the same voltage.
Yeah.
The insert definition then becomes $2 equals Kc dollars, where the dollars is this dielectric constant.
Correct. K is just a number that tells you how much better that material is than a vacuum. Air has a K of about 1, but special ceramics can have K values up to 1,000. This stuff it to store it idea is why modern electronics are so small. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. All right, next up, combination of capacitors. And the most important thing to remember here is that the rules are the opposite of the rules for resistors.
Oh. I remember for resistors, in series you just add them up, and in parallel you add the reciprocals.
Yeah.
So for capacitors, it's the other way around.
Precisely. And our water tank analogy shows us why. When you connect capacitors in series, it's like stacking the tanks one on top of the other. This increases the total effective distance, dollars, between the first plate and the last plate. And what happens when you increase dollars? Remember the formula, Dewey dollars, epsilon A dE dollars.
If d dollars increases, c dollars must decrease, right?
Yeah.
Okay, can you read out the series formula from the book?
Of course. For series combination, equation 2 down in 6EO says the reciprocal sum applies. Frac 1 C eat plus frac 1 C2 plus dot stick.
Now what about parallel? This is like placing the water tanks side by side.
Yeah.
You are massively increasing the total effective area.
And when you increase a dollars, the total capacity, C dollars, increases. The voltage is the same across all of them, but the total charge stored is the sum of the charge on each one.
Let me guess the formula. We just add them directly, right? Like resistors in series.
You got it. Can you read that one out for us?
Yes, equation 2.67 for parallel combination is C equals C1 plus C2 plus dots.
Perfect. Let's do a quick example. Take two 10 microfarad capacitors. In parallel, what's the equivalent capacitance?
10 plus 10. That's 20 microfarads. It gets bigger.
And in series?
It'd be 1 by 10 plus 1 by 10, which is 2 by 10. So you flip it, 5 microfarads, it gets smaller.
Exactly. Series shrinks the capacity, but it allows the combination to handle a much higher total voltage. Okay, finally, let's talk about the energy stored in a capacitor. When you push charge onto the plates, you're doing work against the electric field that's building up. That work doesn't just disappear, it gets stored as potential energy, $10.
And the formula for that from section 2.69 is $1 is Fancy V22.
Yes. Now here's a bigger picture question. Where is that energy actually stored? Is it in the metal plates?
From our earlier discussion, I'm guessing no. It's in the tension between the plates, so
Yeah.
in the electric field.
That is a brilliant connection, yes. The energy is stored in the electric field itself. This is a huge concept. In fact, we can calculate the energy per unit volume, which we call energy density, all dollar. And the formula for that is $1 for epsilon 0 E22.
So the energy is directly proportional to the square of the electric field strength. That really proves the energy is in the field, not the conductor. And you mentioned this links to later topic.
Absolutely. This idea that fields contain energy is fundamental to understanding electromagnetic waves in Unit 5. Okay, now let's tackle 3 exam-killing misconceptions. These are the silent killers that cost students easy marks. Misconception number 1. So many students look at the formula CQ feed and they think, if I increase the voltage V, the capacitance C must decrease.
I can see why they'd think that. It's in the denominator.
It is, but it's a trap. The correct idea is that $T is a constant. It's fixed by the geometry. If you increase the applied voltage dollars, the battery just pushes more charge Q onto the plates so that the ratio V to dollars stays exactly the same. The hook to remember is the size of your bucket doesn't change just because you pour more water into it.
Right. So $2 is constant unless you physically change the capacitor itself.
Exactly. Misconception number 2. We all learned that inside a conductor, the electric field dollars is 0. Many students then jump to the conclusion that the potential dollars must also be 0.
Oh, that's a tricky one.
The correct idea is that if the slope is 0, the height is constant. It's not necessarily 0. The hook is, field is 0, potential is constant. Think of a flat tabletop. The slope is 0, but its height above the floor is not 0.
So the surface of a conductor is an equipotential surface. Its potential is constant everywhere on and inside it. Got it.
And the final one, misconception 3. Thinking the stored energy is simply $1 she times V bol.
That's a very common mistake.
The correct idea is that the energy is $1 frac 12 QV day. You have to have that half. Why? Because when you start charging, the voltage is 0. It rises to a final value $5. The average voltage you work against is only V2. The hook here is it's a triangle, not a rectangle. The area under the VQ graph is a triangle, so you need the 1/2 rule.
That makes so much sense. Average voltage is key.
All right, to lock all this in, here are 3 quick memory anchors for the exam hall. First, the main formula. Just remember the phrase Q equals CV, like a Q for a curriculum vitae. Say it a few times. Q equals CV. Second, for combinations, remember this phrase. Capacitors are contrary. They are contrary to resistors. The parallel rule for one is the series rule for the other.
That's a good one. Capacitors are contrary.
And finally, a physical gesture. Hold your hands up parallel to each other like the plates. Now bring them closer. As the distance dial gets smaller, the capacitance gets stronger. You can do that right at your desk. Okay, so to summarize our entire deep dive into capacitance, here are 3 exam safe points. 1, the capacitance C$ equals QV$ is a fixed constant defined by the device's geometry, mainly area over distance, and it does not depend on the charge $Q or potential $5. 2, inserting a dielectric material with a constant dollar between the plates increases the capacitance by that factor, $2. And 3, the energy stored is $1 frac 12 V22, and this energy lives in the electric field between the conductors. To get maximum marks in 12th CBSE Physics, Chemistry, and Math, visit ProfSam.com.
That is ProfSam.com.
Thank you for joining this deep dive. Study well, and we will see you next time.